can produce X. So at some cyclotron facility, we're going to produce X, let X decay to Y, and then we're going to send Y to a hospital and it will be used there. So the first question, I guess, is you're going to feed X with some rate P, and that'll be like at a cyclotron you're producing it with some rate like maybe 10 to the 10 nuclei per second. You won't have to do, Lee told me anyway, that you won't have to do anything with like cross sections or areal density. If he gives you a rate like this, he'll give you the rate per second and you won't have to try to find that yourself. So what would be the equations that would fundamentally describe the growth or the time-dependent populations of these species without leading, I'll say that it's a differential equation.
So X would be P times parentheses 1 minus e to the negative decay constant times T.
Right, so that's the solution to those, but I guess what I'm asking for is the Bateman equations, right, the differential equations that would describe those, well, where you would find those populations from. How would you write those out?
So it's
Right.
the NDC from lambda or minus lambda.
Right. So you can think of it as the rate of change in the population is equal to some growth term minus some loss term. So in our situation, X is being produced at the cyclotron with a rate T, but X is not stable. So X is going to decay away at some rate, but that rate isn't simply its decay constant, because the decay constant is relative. It's the rate at which a single nuclei decays, which is not exactly a very coherent explanation, but it's basically a statistical number based on decay. So you have to multiply it by the whole population. And so you would solve this differential equation to get the population.
Okay.
So for X we have growth of P and decay of itself at its decay constant. So now for Y, what do you think we would write down? If
Lambda x n, the production, and
right.
Lambda y n.
So we're not producing Y at the cyclotron. The way we're producing it effectively is by letting X decay. So it grows in at the same rate that X is decaying away. Oh, and it's important to put subscripts to distinguish your population. And then just like X, it decays away with some decay constant multiplied by its population. And then for Z, it's a similar situation, but we're going to say that Z is stable, so it's going to grow in with the same rate that Y grows out. And there's no loss term because it's stable and we're not taking it away. Yes.
Yeah.
Yeah. Right. So one thing that might be good to keep in mind is these rates don't necessarily have to be something fundamental, like a reaction or a decay. It might be something like you are chemically extracting the population of one out while it's being produced. So you might want to think about how you would express that in these equations.
Show an example.
It should always be per unit time, right? Whatever
Right.
you put on the right.
Yeah, so it should always be a per unit time. Right.
Everything should be per units or what? Could you like do whatever you were just doing? You know, you just
So let's say, actually that.
let's say if you're extracting, like, so you have lambda x and x, so that's the decay. So then you're extracting at a certain rate, it's not going to be 100% efficient, so that's just the coefficient for the dn, y, or dt. You
Right.
just take that coefficient times lambda x.
So say, because y is our isotope of interest here,
It's the coefficient of extraction.
we would say, let's say we were going
So
to.
you add another wall term.
Right. But you should think about how, so it might be L, but you might want to think about how you might calculate L. It just depends on the problem.
Yeah.
It shouldn't be too hard, but it's important to keep in mind that
make sure it's
if you were extracting Y as you were producing it, but it's also decaying, you're going to have it being produced, decaying from nuclear decay, but also disappearing from some chemical extraction.
So that's like a process loss.
Right. Yeah. I guess the big takeaway from this is not every one of these terms is something physics related. It could be something that you're doing to the population.
Yeah, he's not showing an example.
So let's so now our isotope of interest is y, so we want to solve for y as a function of time, its population. I don't know what Lee is planning for on this. When I took it last year, you were able to write down the solution to these equations on your equation sheet and just use them. But he might, on one of the homeworks, I think Andrew expected you all to derive them.
And then Jaden was like, don't ever do that. That's
Right.
a waste of time.
Right.
On your formula sheet.
He
Don't be
said
stupid.
that
That's what
we
he
would
told me.
not need to do Laplace.
Yeah.
Or if
Because
or
someone
if
asked
we did,
him
he
in
would give it to us.
class.
Yeah, he said he would give us the table.
Okay.
But Jaden also said, do not ever solve differential equations in this class. And I was like, okay, I guess.
Okay,
We don't
well,
want a lot of things.
um,
Yeah, that's true.
I won't speak for Lee, but at least
Write those.
you should definitely have the solutions written on your equation sheet. Because someone will almost certainly ask you to solve for one of these items. And if you were to derive it, I can almost guarantee you that you wouldn't have to derive Z. Y is the most complex equation that you would have to find. Does anyone want to go over finding Y, or are you
Yeah.
okay with just
Particular
sure?
solution.
Okay. Cool. Okay, so we have our first differential equation. And so this differential equation has a solution, and in that solution is an undetermined coefficient. So we'll have to handle that before we move on to the next equation, because we're going to substitute this equation into our equation for y. So this is the general solution, and we have C1 being the undetermined coefficient. So we need some condition that will allow us to determine what C is. And right, the best one is always to say there's no population at time t equals 0. So we'll apply the condition that at t equals 0, n of x equals 0. So let's write that out and solve for we can solve for C1. we have this expression. It's always nice to pick t equals 0 because you can eliminate your exponential. And so then you have c1 plus the rate over the decay constant equals 0. And so simply c1 equals that. And so that gives you a new expression for your population as a function of time. Alright, and so you're probably used to seeing it in this form, which you can convince yourself that that's just factoring out the rate. So then we had our equation for, is everyone okay with this, or should I leave it up? I'll do it over here. So we had a differential equation for y, and that is, dependent on the population of x. And so one thing that I've seen that's kind of tricky is people will try to solve this differential equation on its own and then plug n of x into that solved equation, but that's not something that you can do because you don't account for the time dependence of n of x. So you need to plug in this expression for n of x. And then you can get rid of terms, and you have your kind of nice but not really nice differential equation. And so that has a solution. Is everyone okay with this side now? So again, you have another undetermined coefficient, and we'll apply the same condition that at time equals 0, we have no y.
Wait, so why is it lambda x minus lambda y on the bottom of the center two terms?
Yeah.
Okay.
Yeah.
Okay.
Yeah, I will say that I hope he doesn't put something like this on there, and
You mean hope he doesn't require us to like
right,
derive it?
yeah, that's what I should say, that you,
Okay.
I hope you won't be required to derive it, but it's always good to be familiar with it, nevertheless. Well, anyway, you're going to have all these terms again. These aren't time dependent. And you're going to have C2 and you're going to solve for C2 and C2 convenient about this is when, oh, I'm sorry. Actually, you know what, I need to write that out. I forgot there is time dependent. So this becomes 1, and so then you have plus px minus py minus py, and these terms cancel out, which is convenient. And you solve for C2. Sorry, that's really messy. And you'd plug that back into your expression for NYT, and through a bunch of moving around of variables, you'll eventually get what you find in Crane. Oh yeah, you're right, sorry. And this is what you've seen in Crane. So what's important is that you should have this equation and this equation and maybe a third equation. I don't know if that's in Crane on your equation sheet. Or actually, if you don't have the third equation, maybe write down the general combinatoric solution. Because if you were to find the next step, you can start to notice a pattern, and you don't have to derive
Is that first
every
lambda
one.
1? Is that lambda 1? The first lambda right next to P?
Here?
Yeah,
First.
right. Right next to P.
Oh, you're right, you're right.
I don't know.
Yeah.
Lambda X, right? I don't know.
Yeah, I think it. Let me see.
And the one in the first term is not a gamma, right? The Y up there.
Yeah, sorry. Or I think that's an X, yeah.
Alright.
Cool. And so now that you have your expression for y, you can solve for the time-dependent population of y. I guess what's important to note is that this is the time-dependent population of y while x is being produced. So this equation isn't valid if you have, if you're not producing x. If you're looking at just some population of y that is in a somewhere further down in a decay chain where you have some initial population of x, you need a different equation, and basically you would just change the differential equations so that you don't have a p term on x. And I guess you could see how if you were to change p to 0, then there's 0 population y, and so that's not going to be very useful to you if you're using the wrong equation. Any questions? Cool. So I guess the next thing is, say X is toxic, and you don't want a lot of X in your sample when you send it to the hospital, so you need to let it decay away. And you need to find a time at which the population is low enough that it's safe to ship. So let's say the population of X needs to be a safe population with variable C. So how would you solve for the time at which it's safe to send the population out.
Isn't it usually just like 4 half-lives when only 1% of...
Right,
or-
well, if you were going to solve for it analytically.
Oh, okay.
Just plug find activity, so multiply by lambda, and then plug in whatever activity is your
Right.
parameter.
Yeah. And for this situation, you would need, if you were saying that this is after the sample's been produced, you would need to use the different set of equations, the batch. They're often referred to as continuous production Bateman equations. These are the continuous production Bateman equations. The other one is the batch Bateman equations, where you just have some batch of population and it's decaying. There's no production, and so you need the solutions for that. But if we have, if we're looking at X, which is the first pair in the isotope, then it's just simply going to be the normal decay equation that we all know and love. And so you would set this equation equal to C, and you have your n of 0, but where are you going to get your n of 0?
When the production stops.
Right. So you would need to calculate the population of X at the time after the irradiation is done. Is everyone okay with this half of the board? Can I erase it? Okay.
If they give you the same population for it, oh, yeah. Oh, sure. Because you said population. Wait, the population has to be okay, cool. We're all on the same page.
So n of 0 we said is found by we're done with the irradiation, so you need to find the population of X at the end of the irradiation period, and we use our equation from over there where we have and you're going to get exponentials that will cancel out. Or, sorry, not cancel out. Combine. We'll leave it there. So you have this as equal as some, say, population C. We can move our constants to one side. And so, I've seen this catching people before. How would you then get T out of this side? So we're solving for T.
Right. Why can't you just do that at step 1, solve for it? Like take the natural log of both.
You could. It's a little bit easier if you get it down to a step, but you could. But you mentioned it. Take the natural log of both sides of the equation. And then from there, you can pretty easily solve for it.
I'm really confused about so I would have just done the first step, like C equals n naught e to the minus. What did you do under that? Because why do you have production and stuff?
Okay, sorry. Yeah, I should have, I accidentally added continued the line when I shouldn't have. So n naught, we said was our population after we're done
production.
Oh, that's just gonna be like a constant, right? Like,
Yeah, but you need to calculate it.
oh, so you're showing how you calculate speed. Oh, okay, okay, I
Yeah.
got it. Alright.
Radiation time.
Alright, cool. Thank you.
It's not time zone.
And
All different times.
I had included one where I would have given you numbers and we'd walk through it, but I haven't crunched the numbers on those, so I'll just post it tonight. I trust that you all are competent enough to crunch numbers. So.
Question?
Uh-huh.
When you take the natural log of both sides, I never didn't think that was how you could do natural log like that. I thought you had to combine your e's first, or can you do it like that?
I don't think you can combine them at this step.
So, but like if you, let's say you just had them as normal numbers, like 2 minus 4, you said, okay, we're going to take the natural log of that side. The natural log of 2 minus the natural log of 4 isn't equal to like the natural log of the.
Right.
Okay.
It's gonna be the, and the t's are gonna cancel out after.
Yeah, isn't it going to be a lambda? I think there's something a little weird. I think you're supposed to divide them.
I think you are combining
I think
the
your
e's.
two t's are different and they're in the same problem. Like you should
Oh,
have a t in
you're
a
right,
time,
you're
or
right,
like a t in
you're
a
right.
tau.
Yeah.
The production t should be a
I
t
think
dot.
what you should do is just take the natural log of both
Right.
sides of that first equation you have, and then just assume you already
Right.
found n on it.
Yeah. So, yeah, my bad. I should have included a T0 up here.
There you go, yeah.
Yeah, because this T is different than this T. This is the time at the end of the irradiation sweep, and then this is the time after you stop the irradiation.
Damn.
I'll fix this equation tonight, and you'll see it on the solution sheet.
They would, but they're different t's.
Yeah, they're different
That's the
T's,
point of the
so
story.
Yeah.
don't look at this, and I'll post something tonight. Any questions about population? Okay, so I'm going to move on to the beta-Weizsäcker formula, and then after that, that's all that I have for specifically prepared questions, but if you all have questions, I can try to field